So now that we've gotten some double integrals in both Cartesian and polar coordinates, we're going to spend a little time here delving into applications of them. And today, the first application we want to use is talking about the density, mass, and then finding the center of mass of objects. Now, in this case, because we're still only dealing in 2D, remember, we're going to do all of our double integrals, everything in 2D, before we kind of step into the world of 3D. What we're doing is we're looking right now at something called lamina. A lamina, as its name might suggest, like a laminated or something like that, something that's laminated. A lamina is just a sheet. So this is like just a strictly 2D shape. So you might imagine that a lamina is, a sheet of some material or, a very thin piece of metal or something like that. So we're going to talk right now about these lamina. And one thing that we want to do is we want to be able to define this idea of density. What do we mean by density? Well, density, just generally speaking, is kind of how much stuff is there, how much mass is there per unit size, right? You can define a lot of different types of densities, actually. For like a wire or something that's long and thin, where we're mostly concerned about length, you can have what's called a linear density, which is mass per unit length. For a sheet like we've got, you can have a density. Sometimes they use sigma for this. We're not always, which is a mass per unit area. And then for like a 3D object, you can have a density, which is a mass per unit volume. In this case, we're going to develop this mostly thinking about this second category of sheets, of things that have a mass per certain area. Now, we're not going to use sigma here. We're actually going to use the more general character for density, which is the Greek letter rho, which is, you've seen from spherical coordinates. Here we're repurposing it. And one way to think about rho is that it's kind of, if you take a little bit, of area sort of delta A, it's like the limit as that delta A gets smaller and smaller of sort of how much mass is in that divided by delta A, that ratio. So we can actually define a function that tells us the density at any point. And now some objects, right, if it's made of all the same stuff, this might be a function that's the same everywhere. But you can imagine having a sheet that's maybe made of different materials or that's thicker in some places than others. And so the density could be different. The density could change, right? You could imagine having a sheet that's got, a heavy side and a light side. Not every object is made of has constant density. So what if we have an object with some density function, right? And we want to figure out what its total mass is. Well, if I want to figure out what its total mass is, right, I'm going to probably have to add some things up. So what I could do is I could instead ask how much mass is in this little bit dA. Well, and in that little bit dA, assuming that my my area is small enough, I can just multiply my density times dA, and then add all those up. So when I'm doing this double integral of rho dA to get my mass, and I'll go ahead and put that over here as kind of a key equation. When we're doing that double integral, what we're really doing is we're saying, I'm going to multiply my density by, how much mass is in here, how much mass is in here, and here, and here. We're going to add up the density times area for each of those little bits. So let's do a quick example of this. Here we've got a little triangular lamina. Let's say that this is a chip. It's a tortilla chip. And it's kind of triangular. It's got, a corner at the origin at 0, 2, and at 2, 0. And it happens to be dusted with different amounts of cheese powder in different places. It's not even, such that the density is given to us by this function 1 plus x plus 2y. So as we move along our chip in the x and y directions, the density changes. It's got different amounts of mass in different places. So if I want to find the total mass of my chip, I have to do a double integral of my density function, dA. I'm just going to arbitrarily choose to do this dy dx. It's, you could do it dx dy if you want, doesn't matter. In this case, if I do y is going to go from 0 up to this line. This line is y equals 2 minus x, and x gets to go from 0 to 2. So I'm just integrating my density over this. So we can bust out this integral real quick. This ends up being y plus xy plus y squared from 0 to 2 minus x. When I plug in 0 for y, I get nothing. So I really just need to worry about 2 minus x plus 2x minus x squared. Plus, and if I FOIL this out, I get 4 minus 4x plus x squared. A couple funny things happen. My x squared terms cancel out. And I get, if I tote all this up properly, I get 6 minus 3x dx. This is just the details of actually doing the integral. That gives me 6x minus 3 halves x squared from 0 to 2, which is 12 minus 6. So the total mass of my chip, in whatever units I've chosen, is 6. All right, so if you're finding mass, double integral of rho dA. One of the other things you can do is you can also use this to find center of mass. So the way that you find the center of mass of an object is that you take a weighted average, and we'll go through in class a little bit deeper into the derivation of this. But if I want to find the x-coordinate of the center of mass, what I'm going to do is I'm actually going to take a double integral of x times rho dA, and then I'm going to divide by my total mass at the end. And so the idea of this is I'm basically, again, taking an integral over my whole shape, but I'm also asking, hey, what's the x coordinate of each little bit of mass? And in this way, it's a weighted average. So the y coordinate of my center of mass, we're going to find y times rho dA. And these are also really important. We're going to be using this a lot. We're going to be finding a lot of centers of mass. Now, I do want to note that means to find the center of mass of an object typically takes 3 integrals, 1, 2, 3. The more that you can reuse these numbers, the better off you are. So, or the more that you can exploit symmetry. So we will often find in class ways to avoid doing one or more of these integrals. We're not going to avoid it right now. So we're just going to charge right in. So we'll do the full treatment for finding the x center of mass. So if I find the x center of mass, 1 over m, x times my density, still going to do it dy dx. My bounds are the same because my chip is the same. So you still get 1/6, 0 to 2. And in this case, I get xy plus x squared y plus xy squared from 0 to 2 minus x dx. All right, so I got to be a little cautious here. Again, when I plug in y equals 0, I get nothing, so I only need to worry about the 2 minus x part. And I'm doing a lot of distribution in my head, so when I plug in 2 minus x here, I get 2x minus x squared plus 2x squared minus x cubed plus 4x minus 4x squared plus x cubed. Once again, I got to kind of gather up my terms. My x cubes go away, and I end up here with a very similar looking integral to my mass integral, except that it's 6x minus 3x squared dx, which isn't really so surprising, right? I multiplied my original integral by x, but because the first one I'm doing is dy, it doesn't really make much of a difference in my final answer. So I just, instead of 6 minus 3x, I get 6x minus 3x squared, which does give me 3x squared minus x cubed from 0 to 2. That's going to be 12 minus 8, or 4 over 6. So what this tells me is that the x coordinate, 4 over 6 is of course 2/3. The x coordinate of my center of mass is somewhere along this line. X equals 2/3. If you work it out for yourself, if you do the whole y coordinate, the y coordinate turns out to be 7 over 9, which is, about 0.77777777. So it's a little bit higher. So the center of mass of our chip is right about there. Notice, by the way, why is the y center of mass a little bit bigger than the x center of mass? Well, look, our density is a little bit more sensitive to our y coordinate. That is, if you look at the density right up here at this corner, where x is 0 and y is 2, it's going to be a density of 5. Down here, it's only a density of 3. So more of the mass of our chip is towards the top, which pulls the center of mass up a little bit. So we're going to be doing plenty of these calculations in class. And again, we'll go through a slightly deeper derivation of where they come from. And then once we're comfortable with mass and center of mass, we're going to move on to calculating rotational inertia around a variety of axes. We'll actually prove, for those of you in physics, we'll actually prove the parallel axis theorem, which will be fun. And we'll also do a little bit of 2D probability, which is probably one of my favorite silly topics in multivariable. So, all right, see you in class.